Good morning, everyone. So, in today's topic, we'll be talking about the scattering of light, or how does light interact in our environment or our surroundings. Let's get started with the objectives. Understanding the physical phenomenon. Explain what the scattering of light is, focusing on how light interacts with particles and why phenomena like the blue sky or why does the clouds look white. Next, work through the mathematical formulations of Rayleigh and May, and the third type of scattering, we'll get to that later, solving the respective equations step by step to comprehend their application. And lastly, by the end of this presentation, learners will grasp the fundamental concepts of scattering and its real-world applications. The overview. The presentation explores the scattering of light, covering its concepts, mechanisms like the Rayleigh and May scattering, various applications in nature and technology, and by the end of this presentation, of course, you will gain a deeper understanding of light's behavior and its significance. So first off, there are three types of scattering, namely Rayleigh, May, and Raman. My colleagues will continue to discuss the further types. We'll get back to you later.
Now let us take a closer look at Rayleigh scattering. So Rayleigh scattering, this phenomenon occurs when light interacts with particles that are much smaller than the wavelength of the light, like the tiny gas molecules in our atmosphere. So the mechanism involves the light being absorbed and then re-radiated by these small particles. However, not all wavelengths are scattered equally, so Rayleigh scattering depends strongly on wavelength. So shorter wavelengths, like blue light, are scattered much more intensely than longer wavelengths, such as red light. So, which basically means that the shorter the wavelength is, the more scattered it is. So, this explains why the sky appears blue during the day and turns reddish during sunrise and sunset. So, next is mathematically, the intensity of scattered light is given by the equation I is proportional to, open parentheses, 1 plus cos squared angle, close parentheses, divided by wavelength to the power of 4. So, I here represents the intensity of the scattered light, angle is the scattering angle, and wavelength is the wavelength of the light. So this wavelength to the power 4 relationship shows that as the wavelength decreases, the scattering intensity increases dramatically. So next, to better understand this concept, let's solve a simple example. So suppose the intensity of scattered blue light with a wavelength of 450 nanometers is the initial intensity. So we want to find the intensity of red light, which has a longer wavelength of 650 nanometers under the same conditions. So we use the relationship I1 divided by I2 is equal to, open parentheses, wavelength 2 divided by wavelength 1, close parentheses, to the power of 4. So substituting the values, we get I red over I blue is equal to, open parentheses, 450 divided by 650, close parentheses, to the power of 4. So when we calculate this, we find that the answer is, if you would like to calculate, so the answer is 0.228 times the initial intensity. This means that the intensity of scattered red light is only about 22.8% of the intensity of scattered blue light. So in simple terms, blue light is scattered nearly 4 times more than red light, which is why the sky appears predominantly blue to our eyes. That's all. Thank you.
Why are clouds white? The answer lies in how light intenses with tiny particles around us. So, why do clouds appear white? Clouds appear white because their water droplets are large enough to scatter all colors of sunlight roughly equally, so the combined light looks white in our eyes. So, when light encounters particle about the same size as its wavelength, it scatters differently than when the particles are tiny, and this is what we call the May scattering. But what is the May scattering? So, in the mechanism, light interacts with particles of comparable size to the wavelength of light, and it has the characteristics scattering intensity is more uniform in all directions and less wavelength independent compared to Rayleigh scattering. And it applies by explaining the white appearance of clouds and scattering by larger particles in an atmosphere. Now we have the May scattering problem. So the problem states that a cloud droplet with a diameter of 10 micrometers scatters light. If the incident light has an intensity, estimate the intensity of scattered light as at an angle of 45 degrees. Assume May scattering is dominant and the scattering efficiency factor where Q is approximately 2. And in terms of the solution, the intensity of scattered light in mass scattering is complex and depends on many factors. However, an approximation can be made using the scattering efficiency factor. And the formula for the approximated intensity of scattered light in mass scattering is given as scattered intensity is approximately to the incident light times the scattering efficiency factor over the 4 pi r squared, where the r is the radius, where this icon is the incident intensity and q is the scattering efficiency factor and r is the distance from the particle. The problem provides the following values, where the q is approximately 2 and r is 1 meter, and we have to substitute it to our said formula, and as you can see there, and then we have to simplify it, and we have the final answer, which is the scattered light is approximately to the incident light times the 0.15915, and we have to express this as a percentage by multiplying 100. So from 0.15915 times 100 is approximately 15.9%. Therefore, the intensity of the scattered light is approximately 15.9% of incident intensity.
So in this part of our discussion, we're going to discuss all about the Raman scattering of light. The Raman scattering is the inelastic scattering process where light interacts with the molecule, leading to a change in the energy and directions of light. This phenomenon provides valuable information about the vibrational, rotational, and electronic energy levels of materials. So there are two types of effect. First is the elastic scattering or the Rayleigh scattering, and the inelastic scattering or the Raman scattering. The inelastic scattering, most photons scatter elastically, meaning they retain the same energy and frequency as the indecent light. This type of scattering is known as a Rayleigh scattering. It doesn't provide information about the molecule's chemical composition. While on the other hand, inelastic scattering or the Raman scattering, a small fraction of proton, approximately 1 in a 10 million scattering inelastically, resulting in a change in energy and frequency comparing to the indecent photon. The energy difference between the indecent and scattered photons correspond to the vibrational modes of molecule, providing a fingerprint of the substance. Okay. From the state, several outcomes are possible. The molecule relaxes to a vibrational energy level different from the initial state, emitting a photon with a different energy. The energy difference between the indecent and scattered photons is the Raman shift. Another type is the stroke scattering. The scattered photons has a less energy than indecent photon because the molecules gains energy and moves to a higher vibrational state. Another one is the anti-stroke scattering. The scattered photon has more energy than the indecent photon because the molecule loses energy and transitions to a lower vibrational state. This occurs when the molecule starts in a vibrational excited state. So let us remember that when you say the Rayleigh scattering, it still the energy and the frequency retain, while on the other hand, the Raman scattering has its changes, and also it has two types of scattering, which is the stroke scattering and the anti-stroke scattering. The stroke scattering is the lower energy than the anti-scattering. It's because the indecent photon, because the gains energy and moves to a higher vibrational state. Taas iyang vibration pero low iyang energy. While on the other hand, ang anti-stroke, low iyang vibrational state but taas ang iyang energy. Next. Okay. Problem set. Okay, problem statement. A sample is illuminated with a laser of wavelength 532 nanometer. A Raman shift of 1000 centimeter is observed. Calculate the wavelength of the stroke shift Raman scattered light. Solution. First, convert the Raman shift from centimeter to wavelength unit or nanometer. Using the formula, change in wavelength is equal to lambda squared times change in V divided by the speed of light. Okay, so where lambda is equal to indecent wavelength of 532 nanometer, change in V is the Raman shift 1000 centimeter, and the speed of light is 3 times 10 to the power of 10. Then, okay, so let's proceed to the calculation. In this part is the kanang change, atong i-change into kanang nanometer, from centimeter to nanometer. So muna ni siya ang result, 283 nanometer. Calculate the wavelength of the stroke shift. Stroke is equal to wavelength plus change in wavelength, which is stroke is equal to 532 nanometer plus 2.83 nanometer equals to 534.83 nanometer. Answer, the wavelength of the stroke shift Raman scattered light is approximately 534.83 nanometer.
Hi, I'm back again. So the previous discussions were quite informative, no? Now onto the real-world applications. In atmospheric, the scattering of light creates stunning phenomena like halos, rainbows, and glories in our atmospheres. The very example you can see about this is the sky. Why is the sky is color blue, the clouds why it's white, and there's this phenomenon called aurora borealis. That's a nice phenomenon if you look into it. In medical imaging techniques utilize scattering for diagnostics, improving visualization of the internal body structures. Next would be the optical. Scattering principles are essential in designing optical devices and sensors for various technologies and in everyday life. Scattering explains why the sky appears blue and how fog affects our vision on roads. To summarize the discussion, understanding the scattering of light is very important because it is crucial for grasping various natural phenomena and their applications in our lives. Recognizing different types of scattering, we can appreciate their roles in science and technology, enhancing our connection with the world and the environment around us. Thank you. That's all.